Hi, everyone. My name is Jane Kelleher, and I'm a master's student in Professor Sihong Wang's group at the University of Chicago. I'm excited to share with you our group's work on soft, stretchable pressure sensors for soft robotics and implantable neural prosthetics. Through COVID-19, it's become evident that we're in need of improved technology to improve contactless medicine. Our work addresses 1, the need for contactless teleprocedures, which can be facilitated by medical soft robots, and 2, the need to reduce the demand for residential care amongst patients with chronic conditions, which can be facilitated in part by neural prosthetics to restore lost sensation, function, and mobility. Both of these solutions require interfaces for touch sensation, and to that end, we present 2 soft, stretchable pressure sensors, a strain-insensitive capacitive sensor for soft robotics, and a biocompatible resistive sensor for implantable neural prosthetics. A remaining challenge in the field of epidermal pressure sensors is decoupling sensing performance from substrate strain, especially with intrinsically stretchable materials. Our capacitive sensor has high sensitivity, high robustness, and stable sensing in different strain states. As shown in 1A, it features electrical double layer capacitance using an ionic dielectric, a pyramid microstructure, and stiff microelectrodes and spacers. The capacitance is dominated by the EDL capacitance between the top electrode and ionic dielectric. Pressure compresses the microstructure to increase this contact area and provide a capacitance readout. Contact area that is unchanged by strain enables strain insensitivity. As shown in figure 1B on the bottom right, this is achieved by stiff microelectrodes below the pyramids to reduce deformation and spacers to reduce compression during strain. As evidenced in figure 2A on the top left, our sensor design has a sensitivity of 2.2 per kilopascal. We can see in figure 2B that the signal is virtually unchanged under strain. Responses at 0 versus 50% strain varied by only 2%, which we can interpret as 98% strain sensitivity. Finally, we demonstrated strain-insensitive sensing for remote medical examination. We mounted the sensor on a pneumatically actuated soft robotic hand. As shown in 2C, this assembly could accurately detect applied pressure during flexion of the finger, allowing sustained application of the necessary pressure. We then applied the microstructure design in the context of implantable neural prosthetics, or INPs. INPs, to restore touch sensation after nerve injury, would require a subcutaneous chronically implanted touch pressure sensor with a simple output. To meet this need, we're working on a mechanically and chemically biocompatible contact-resistive pressure sensor for subcutaneous implantation. It employs the same pyramidal microstructure, and as depicted in figure 3B, it features soft, stretchable, and biocompatible sugar alcohol-doped PDOT-PSS electrodes on a PDMS substrate. Additionally, we're replacing typical implant encapsulation materials, which tend to have high moduli or are prone to moisture diffusion, with a novel superhydrophobic fluoroelastomer coating to evade protein and cell adhesion, while maintaining the desirable mechanical stretchability. In conclusion, we're very excited about the impact our work with pressure sensing can have in medicine. Thank you for listening to our presentation, and please feel free to see our brief paper or reach out with any questions.